This video is on sketching polynomials using the first and second derivatives. So we're being asked to sketch the function f of x equals x to the third minus 6x squared plus 9x plus 1. And when we go to sketch this, the first thing we want to do is find critical values where relative extrema could occur, meaning relative maximums and relative minimums. So in this case, the first thing we'll do is look for the first derivative, because to find critical values, you always need the first derivative. So for the first derivative, I have f prime of x is equal to, taking the derivative here, I'd end up with 3x squared minus 6x squared becomes minus 12x, and the derivative of 9x is just positive 9. Plus 1, derivative of 1 goes to 0. So that's your first derivative. Once you have the first derivative, the next thing you want to do is use it to find the critical values. To find the critical values, it occurs when either the first derivative is either undefined or equal to 0. This one here, right, there's no spots where the first derivative doesn't exist, right? There's no undefined areas. So we just want to set it equal to 0 and solve for x. To solve this, first thing I would do is look for a greatest common factor and try to solve this by factoring. And this has a GCF of 3. If I factor out 3, I'm left with x squared minus 4x plus 3, right, and that equals 0. And then 3 in front, just stays in front as the GCF. Factoring the x squared minus 4x plus 3, it factors down to two sets of parentheses, x times x in front, multiplies the 3 and adds a negative 4 would be x minus 3 and x minus 1 as the factors, still all equal to 0. To solve this equal to 0, remember you set each of the factors that has a variable equal to 0. So I set x minus 3 equal to 0. So x minus 1 equal to 0. You don't set this 3 equal to 0 because 3 never equals 0. And then solving each of these, I'll add 3 here, so I get x equals 3. Here I'll add 1 to each side. I get x equals 1. So these are what we called, remember, our critical values. I'll use CV to abbreviate that. So these are our critical values, and then you want to determine if their relative extrema are the maxes or mins that occur there. And to do that, we either use the first derivative test or the second derivative test. It's really, a personal preference. In this case, I'll use first derivative test just to kind of show what would happen. So for first derivative test, basically what we do is make a number line for the first derivative, f prime of x, and we place our critical values on that number line in order from left to right. So I'd put 1 here and 3 here. And what we do is we test values to the left and right of each of these to determine if the first derivative is positive or negative there. And that'll give us information about the original function. So if I was looking for something to the left of 1 to test, maybe I'll say f prime of 0. And it's important, this is an f prime number line. You're substituting into f prime, the first derivative. So f prime of 0, the first derivative is right here, the 3x squared minus 12x plus 9. If you were to sub 0 into here, you just get positive 9 out. The important thing about this, though, is that it's positive. So f prime of 0 is equal to 9. That's positive. The reason this is important, it tells you what happens to the original function there. The original function f, if the first derivative is positive, that means you have positive slopes to your tangent line, so it means the original function is increasing. All right, so don't forget what that's telling you. Between 1 and 3, what value could I sub in? Well, 2 is probably the easiest. You could pick any value, right? But f prime of 2 is probably the easiest. This would give us, remember, subbing into f prime, you'd have 3 times 2 squared. All right, if I substitute into that, it would be 3 times 2 squared minus 12 times 2 plus 9. And you want to evaluate what you get from there. 2 squared is 4, 3 times 4 is 12. This is 12 minus 24 would be negative 12 plus 9 equals negative 3. The important thing, though, is that it's negative. So we know that between 1 and 3, our first derivative is negative, right? Because at 2 it was negative, so everywhere in between it's going to be negative. That tells you what about the original function? Well, a negative first derivative tells you that the slopes of the tangent lines are negative. It tells you that the original function f is decreasing, right? So the first derivative tells you where the original function is increasing or decreasing based on it being positive or negative. To the right of 3, I'll pick 4. You could pick anything. You could pick 1,000 if you wanted to. But I'll use 4 just because it's a close value to 3. We would do 3 times 4 squared minus 12 times 4 plus 9. Again, remember, you're subbing into the first derivative. And you can sub into the factored form, but you have to sub into the first derivative. And this equals, well, 4 squared is 16 times 3 is 48, minus 48, that gives me 0, plus 9. Well, this is a positive 9. The important thing, though, is that it's positive. If the first derivative is positive everywhere to the right of 3, because 4 is to the right of 3, then the original function f, a positive first derivative, tells you that the original function is increasing, right, because the slopes are positive. So that gives us information, right? So if I'm going from increasing to decreasing here, right, that's what this really shows me. Then what happens at 1? Well, at x equals 1, if it's going up as it approaches and going down, then we have a relative max, right, because it's going up then coming down, at x equals 1. All right? And what happens when we go 3? Well, we're decreasing, so we're going downward, and then we're going upward. Well, if I'm going downward and then coming upward, then at 3 I have a relative min at x equals 3, because the graph's function is decreasing and then increasing as you go to 3, right? It decreases as you get to 3 and then increases after, so you're going down then coming up, and so when we have a relative min, we know that at 1 and 3, right, the slope of the tangent line is 0, and that's how we know that it's neither increasing nor decreasing at the exact points. So we found that there's a relative max at x equals 1. We know there's a relative min at x equals 3. Now we want the y-coordinates that go along with that to sketch this. So now we'll find the y-coordinates. To find the y-coordinates here, we're subbing into the original function f of x, right up here, f of x. So we want f of 1, which would give us 1 cubed minus 6 times 1 squared. All right, I'm just subbing into the original function up top. Minus 6 times 1 squared plus 9 times 1 plus 1. And that comes out to, I got 5. You can just do this in your calculator. You don't necessarily have to show the work for it. Just make sure you're substituting in correctly. F of, what's the other value? 3. So we would have 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. This comes out to, if you add that all up, this comes out to 1. Because you got 3 cubed is 9. This will be minus 6 times 9 would be 54. So it would be negative 27. This will be plus 27. Those cancels to 0. Plus 1 just gives you 1. So you've just found the relative max and relative min values. The relative max occurred here, right? So we have a relative max at, this is x comma y, would be 1 comma 5. The actual maximum is what we would call 5. And then we have a relative min at x equals 3. So the point 3,1 is what we have here. So we have a relative min at the point 3,1, right? So the minimum value, they're saying the relative minimum value is 1. So we have that part, figured out for what our graph's going to look like. Other questions we might ask you is, where is f increasing? Where is f decreasing? What intervals? Well, your number line for the first derivative shows you that. You could also get it from your graph later, but it's important to understand that you have this in front of you now. F is increasing. Well, what intervals? Well, from negative infinity up till 1, right? And from 3 to infinity. Remember, you don't include the endpoints on this. It's not a union. It's just saying which intervals does it increase on, right? So negative infinity to 1 and 3 to infinity. Where is it decreasing? Well, f is decreasing on the interval from 1 to 3, right? You get that straight from our f prime number line, right? It shows us that the first derivative was negative there, so that's where it's decreasing. So this is information you have to help you graph, right? You can use this later on. So we found the relative extrema. We also want to talk about if there's any inflection points on our graph. Now for inflection points, we're going to look at the second derivative. So I want to find f double prime of x. And we either set it equal to 0 or find where it's undefined. In this case, you know, our first derivative was equal to 3x squared minus 12x plus 9. So our second derivative will be equal to, taking the derivative of that gives us 6x minus 12. This never becomes undefined, so you don't have to worry about undefined points, although if there were any, you'd use those as your critical values, or your possible inflection points. But you set this equal to 0, and you want to solve for x. This will give us a possible inflection point. So we add 12 to each side here. I end up with 6x equals 12, and then divide by 6 and divide by 6. I end up with x equals 2. This is a possible inflection point at this stage. You have to determine if this is an inflection point or not. Well, how do you determine that? Well, similar to what we did the first derivative test, you make a number line for f double prime. Now, this is not called the second derivative test. Right? Second derivative test is something you use to determine maxes and mins. This is just how we determine inflection points. So if I did a number line for f double prime of x, I want to put my possible inflection points on there. In this case, there's just one of them, 2. And I want to test values to the left and right. Well, something to the left of 2, I'll just choose 1. So let's say I had f double prime of 1. Well, that's 6x minus 12, so it's 6 times 1 minus 12. So this gives me negative 6. The important thing here, though, is that it's negative. So this tells me that the second derivative is negative to the left of 2. What's that tell you? If it's negative to the left of 2, it also tells you that the original function, right, f, is concave how? Well, it's concave down to the left of 2. And to the right of 2, I'll pick a point. Maybe I'll pick 3. So f double prime of 3 is equal to, now you could have picked any value you wanted to the right, but it'll be 6 times 3 minus 12. 6 times 3 is 18 minus 12, so it's a positive 6. The important thing is that this is positive, so that I know everywhere to the right of 2, the second derivative is positive. And so what happens with the original function then? Well, if the second derivative is positive, then f, everywhere to the right of 2, will be concave up. So this went from concave down to concave up, so x equals 2, right, went from being where the possible inflection point occurs, that we know the inflection point occurs there. So we have an inflection point at x equals 2. You know this because the concavity changed there. Now we also want to talk about the y value that goes with this. The y value, right, would be substituting back into, right, so the y coordinate, you saw back into the original function f of x. So we're looking for f of 2 here. The original function is what we had at the very beginning, the x cubed minus 6x squared plus 9x plus 1. So substituting that in, you would have 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1. I would like to see this part, but you don't have to show me all the algebra that goes into evaluating that. 2 cubed is 8 minus, this will be 6 times 4, so 8 minus 24 gives us a negative 16, plus 18 would be 2 plus 1. This gives me 3. So the inflection point has coordinates 2, 3. So that's a point on our graph that we know about. We also know about the intervals where concavity changes, right? That's what this number line really tells us about when we do a number line for f double prime. We know that our original function is concave up everywhere to the right of 2. So it's concave up from 2 to infinity. We know that our graph is concave down everywhere to the left of 2, right? So everywhere from negative infinity up until 2. So we could ask you questions about these, where what's the concavity, or the intervals where it's concave up and concave down, but also understanding that, you know, it's given to you in the number line. You find that as you do it. A couple other things to point out here before we sketch the graph. One thing I wanted to point out is that if you were to do the second derivative test to find the maxes and mins, rather than doing what we did up here for the first derivative test, what you would have done to find the second derivative, to find the maxes and mins, is use the second derivative and then substitute the values in. Well, if I substituted the critical value of 1 into the second derivative, that's what I would have really done right here. It's actually what I showed already. If you did that to find the relative max or min, what would happen is, okay, second derivative of 1, it came out negative. That means that we are concave down. If we're concave down, what kind of point is that? Well, that's a relative max. And that's because I subbed in 1, my critical value, and I know it has to be flat there. So it's either going to come down to it and go up, or go up to it and come down. Because it's negative, I know I'm concave down, so the flat part has to be where the max occurs. And that's what we found, right? We found that x equals 1 was a max from over here. Some people prefer second derivative test because it's a little faster, but it only works if, you know, this second derivative comes out to a value that's not 0. The second derivative evaluated at 3, we got something that was positive, right? So when I subbed in my critical value of 3 from above, I got something that was positive down here. Positive tells me that my graph is concave up. If I'm concave up, well, that's a relative min. So it's another way of determining if your critical values are relative max or relative mins. This would be what we would do when we were trying to find the second derivative test, or use the second derivative test to find maxes or mins. The last thing you should use when you're graphing, just because it's easy enough to find, is the y-intercept. We won't worry about finding x-intercepts because they don't always come out to rational numbers. But the y-intercept, to find that you set x equal to 0 in the original function. Well, if I set x equal to 0, I'm looking for f of 0 here. I'm going to get 1 because all of these terms that have x in it go to 0. So f of 0 equals 1, which we know from substituting in. So the y-intercept has the coordinates 0, 1. So once I have all that, we'll sketch the curve. All right, so we're going to sketch this graph. I'll do it on the next sheet so we have some space to work with here. Sketching this, all right, we're going to have an x and y axis. So here's x, here's y. And we'll plot some of the points that we just found. So let's put the relative max and the relative min on there. So the relative max was at 1, 5, and the relative min was at 3, 1. So 1, 5, so 1 up 1, 2, 3, 4, 5 would be right there. And we said that's the relative max at 1, 5. The relative min we said was at 3, 1. Well, the x value is 3, the y value is 1. So right here, that's the relative min at 3, 1. We also found the inflection point where the concavity changed. That was at the point 2, 3. So the x value of 2, the y value of 1, 2, 3. So that's the inflection point at 2, 3. And we found the y-intercept. So y-intercept was 0, 1. That was the last piece we found. Right, subbing x equals 0 in, you get a y value of 1. So you're here. And then we are going to sketch this graph. Now, we know information about it. We know that this graph is increasing, right, from negative infinity to 1. You can actually see it on our number line. So we're up until we get to x equals 1, this graph is increasing. We also know that this graph is concave down all the way until we get to 2. So I know that I'm increasing and I'm concave down up until 1. So increasing and concave down everywhere up until 1. All right, so that's increasing and concave down. Then at 1 you start decreasing. It's a relative max. You should know you're going back downward. It also shows it here in the number line, right? So we're decreasing and we're concave down until 2. And then once we get to 2, we're still decreasing, but then we go to become concave up because that's the inflection point. So you go up, hit your max, you're concave down until you hit the inflection point, and then you start bending upward. When you bend upward like this, you're going to be concave up, right, the rest of the way from 2 to infinity. So we're concave up the rest of the way through. This is a relative min, so you can't go below it, and then we're concave up forever. And notice, after x equals 3, we should be increasing. So the shape of this in terms of increasing and decreasing should come out based on knowing that you have maxes and mins. Arrows on the ends of these because it does go on forever in both directions, and this is our graph of f of x equals x cubed minus 6x squared plus 9x plus 1. So You know, another example here, just showing how to use the first and second derivative to sketch your graph. If you had found the maxes and mins using second derivative test, it still would have worked exactly the same way. You may not have been able to answer the increasing and decreasing questions as easily. You would have had to look at your graph and then tell me the intervals where it's increasing and decreasing. So hopefully this video helps.